Hi everybody, my name is AREA2022 and I want to present to you a work done by myself and my colleague Dan Swissa under the supervision of our advisor, Professor Brafman. So we will review some background and motivation regarding robotics and AI planning, existing systems, the gaps we found, our contribution, an experiments video, and an illustrative example. Let's start with a short recap on AI planning and POM-DPs. So AI planning, it can solve a planning problem, and this planning problem can be described in a variety of ways, and POM-DP is one of them. In POM-DP, the agent is unaware of its current state. It maintains a belief state, which is a distribution over states to reflect its belief on what is the current state. The transition between states when it applies an action is probabilistic. And after it applies an action, the environment changes its state and it receives an observation. This observation hints the agent, it allows it to update its current belief. And it also receives a reward. This reward is conditioned on the next state and the action that was selected. The goal when you are solving a POM-DP is you want to maximize the total expected accumulated reward. So you want to find a policy that maximizes it, and this is your goal. And we think that this model is very good for robotics. Why? Because robots they have partial noisy sensing of the world, so they are not fully aware of the real state of the world, and because they are physical agents, then it's very likely that their actions are not deterministic. When we want an AI solver to solve a POM-DP, then we need to describe the POM-DP. There are two ways to do it. One is an exhaustive description. This is suitable for very small problems. Just for example, if we have a problem with 10 Boolean state variables, then the size of the state space will be around 1000, and this is hard to describe manually. And also the transition function for a single action, it will be a table of around 1 million cells. So this is practical. It's only good for very small problems, but it's not practical for the interesting problems we want to solve, especially in robotics. So what do people do? They use action description languages called ADLs, and in here we see an example of a transition function described in RDDL. RDDL is a language to describe POM-DPs, and it's a very rich and expressive language. In this example, we see the wildfire domain. It's a 9 cell grid. Each grid can have fuel or not have fuel. It can be a target cell or not, and it can be burning or not. And in here, the code example we see, this is the transition function, and we can see here that we can describe if a cell is burning or not, and we can describe conditions using if-else. And we can see that it's also conditioned on putout. Putout is an action that the agent can select, so it will change the result of the value of this state variable. And also we can describe a probabilistic action by sampling from a known distribution, in this case a Bernoulli distribution. So in here we can compactly describe a not so small domain using a very compact description. We have a claim about the current ADLs, and we think that they are not expressive enough for robotic domains especially. Robotic domains, these are real world problems, and you need the expressiveness to describe them. So just to give an example, in RDDL, which is very expressive, we don't have while loops. What does it mean? It means that if I want to describe a skill that how it changes the world, it continuously samples a random cell, and if this cell meets certain condition, then it says that it is burning, and then the skill stops. And if this sample cell doesn't meet the condition, some conditions on it, then it will continuously sample new cells. Because RDDL doesn't have while loops, then they can describe it. They can use if-else expressions, but this is only good for very small example. It can be possible in this 9 cell grid, but not for larger examples. This is one example, and another example is because we are limited in the data structure we are using. Let's say that we want to describe a domain, that in our domain, the cell neighboring can change dynamically. In RDDL, you need to exhaustively describe all of these objects, that they are described the neighboring cells, and then you can have conditions on them. But what if the links, the neighboring links, they can change dynamically? Maybe this cell can then be linked to another cell, and then it can cause it to burn. In real world, we have this. We need this flexibility, and this is not something we can describe in RDDL. So we have this expressiveness problem. And another thing, when we are talking about robotics, then after we selected an action we want to perform, let's say we want to put out a grid cell, then still this is not enough to activate robot code. To activate robot code, we need to add an additional mechanism that will translate this action selection to activating the robot skills with the correct parameters. And also after we will receive the result from this robot code, we will need to translate it back to something that this planning domain can handle, so that the solver can reason about the observation, the actual observation from the environment. What we saw is that probabilistic programming languages, they can compactly describe complex probabilistic domains, models. And what we think is needed is to use a general purpose programming language to empower an action description language. Why is that? It's because that programming languages, they are used to solve real-world problem, and the engineers are using them successfully, and they are very mature. We are talking about C++. C++ is also widely used in robotics. C++ has a large set of implemented code for constructing and manipulating data structures, and because of that we can easily describe the two examples that I showed you that RDDL cannot describe. Regarding the abstraction gap, this we will talk further on. Okay, so let's talk about the current state of affairs in robotics today. We interviewed engineers from 2 large companies working on autonomous robots, and we saw how they are doing it. So first of all, the robot programmers implement robot skills, things like navigation, object detection, arm manipulation. These are the basic skills of the robot. Then they write a script which is used to schedule the different basic skills to reach a certain high level objective. So this is how it's done, but it's not simple. Why? Because robots are physical agents, and the actions they are usually not deterministic, and also they don't have a perfect view of the world, so it's very hard to write a script that reasons about all of these changes. And even after they succeeded to write such a script, if something changes, like in our example that we can see, if the basket the robot is placing the toys inside, if it changes to 2 baskets, or maybe the arm was changed, then they need to write it over again. So this is not simple. So why don't they use AI planning? The reason they don't use AI planning is because there is a significant integration effort, and this integration effort it concerns the expressiveness missing in ADLs, and also about this gap between low-level robot code and the abstract models used for AI planning. So if we want to use current systems, what are our options? The available general purpose AI planning robotic systems are ROS-Plan, which was the first. It supports PDDL, which is can describe deterministic planning, which and if the robot performs an action and we have something which is unexpected that occurs, then we need to perform replanning, and this can cause a repetitive behavior of the robot. They also support RDDL, but in a limited way, not supporting noisy sensing or partial sensing of the world. They also require significant integration effort. We saw it while experimenting with their system. So their system is good, but it has its drawbacks. There is also the CLIPS executive system. This system has a predefined high-level plan in the form of a goal tree, and every time they know the goal that they want to pursue, and this goal is represented using PDDL, and the PDDL planner is activated, and by the result of the plan, then they know how to traverse inside the goal tree and to pursue the next goal. And we have the skill-based architecture. They propose a formal language to specify robot skills. They allow code auto-generation to assist the integration phase, which is very good, but the programmer still need to write some code. They also use PDDL, which, as said, it's only for deterministic actions. So the gaps we found. First of all, current ADLs, they are not expressive enough, in our opinion, for real-world robotic problems. And I just heard about a professor which is very disappointed that in RoboCup home no one is using AI planning. So maybe this is one of the reasons. We also saw that there is an abstraction gap between planning problems to low-level robot code. So this is something we need to bridge. The available systems, most of them don't support probabilistic planning, and even the ones that do support, they don't support noisy sensing or partial sensing of the world. And the current systems, they also require the users to write code that teaches the skills to the system, and this integration effort, it deters users from using the system, and we want AI planning to be accessible. And also we want our solution not to be tightly bound to any specific robotic system. So what is our contribution? We introduced the AOS, the Autonomous Robot Operating System. It's part of a wider vision we have. It's a complete methodology and tools to automatically bridge the gap between basic robot skills and AI planning. In our solution, the user only need to supply documentation for his skills, and it's a plug-and-play solution. Everything will work automatically. The code that teaches the skills of the system will be automatically generated. So how it will be described? We have our ADL, which is called GSDL, short for Generative Skill Documentation Language, which is empowered by C++. And this describes the planning model, and we to bridge the gap between low-level code to the planning model, we have the abstraction mapping. It's another documentation that every skill will have, and this maps, tells the system how to activate robot code based on an action that was selected, and also how to translate the response from the code to an observation that the solver can reason with. And that's it. Let's talk about the system architecture quickly. We have the AOS Web API. This is the gateway for the user to interact with our system. It can send HTTP request, and once it sends a request to integrate his documented code, then we auto-generate sections into components. One of them is the functional layer middleware. This component is responsible to actually activating the robot skill, and so based on the abstraction mapping documentation, we generate this component. And also it listens to public data inside the functional layer, so to help it to calculate the observation. It not only relies on the response from the user code. It can use additional information if the user decides to document it. And we have our planning engine. The planning engine select the next skill for execution, and we are using sampling-based techniques. Now these techniques, they require a high sampling rate, and we saw that if we are using a generic code that can handle all of the domains, then the sampling rate is dramatically reduced. We checked RDDL Sim, which is an open source code used for the international planning probabilistic planning competition, and we saw that it can be 40 times slower in the sampling rate from our auto-generated code, which is it makes sense because our code, it's only for a specific domain, so it's a lot more efficient. Let's look at an experiment. Okay, so this is the Panda robot, and in the experiment we did in our lab, we implemented two basic skills. One is that we can draw a circle inside a tic-tac-toe cell, and the other one is that the robot can detect the state of the board changing. So after documenting these two basic skills, we also documented inside our environment file the desired states and the undesired state, and we saw that things are working smoothly, and the integration is easy, and we see that the robot is acting in a sensible way. In our second experiment shown here, we are showing on an armadillo robot. We have a real one in our lab, and this is using a gazebo simulation. In this experiment, we are showing a peak basic skill which is not probabilistic. It can succeed or not, and also it returns a noisy observation. And we documented this along with additional skills, and we see that it's easy to document, and also if by experiments you are seeing that things are different, it's easy to change the documentation, and we see that the system is also working smoothly with reasonable results. Okay, let's look at an illustrative example. In here, we just to get the look and feel of the system. We have a robot with a single navigation skill that needs to navigate as fast as possible to 3 known locations. Now this navigation skill can fail with a chance of 10%, and also when it fails, only in 80% of the chance it reports that it actually failed, so it has also noisy observations. We will start from bottom up. We can look at the abstraction mapping file, and this file we can the user documents how to activate the navigation skill. In ROS, we are using ROS services, so we have the pass and the low-level details to actually activate the code, and this can be conditioned on parameters sent by the planner. And we also describe the observation that are possible from when activating this skill, which is success and fail. Now they are sent and they are conditioned on local variables. What are these local variables? These local variables, they can be defined and conditioned either on a response return from the robot skill or from public information in the framework. Like in ROS, you have topics that are currently publishing information from processes in the environment, and in here we are saying that if ROS out, which is the log, it publishes that the goal is reached, then we know that this goal reached is receiving a true value, and then we can send success. This is the environment file. We can describe that we want to visit the 3 location and that it is a goal state. And in here in the GSDL, we can describe how the state changes when we activate this skill. So we are saying that the robot location, it changes, it can fail in 10%, losing its orientation, otherwise it goes to the discrete location that was sent to the action. We can describe the model response. This is our observation model, which can be noisy. We are describing it using a Bernoulli distribution. Everything here is C++, so it's very expressive. And also the cost when applying this skill, you can also describe it. In here it's the distance. So a summary and future work. The AOS is a complete set of methodology and tools to bridge basic skills and AI planning, and it is a plug-and-play solution. We introduced our C++ powered action description language called GSDL, and our abstraction mapping to bridge the gap between low-level code and AI planning. For in the future, we plan to do in the near future a user study on the AOS. We want to implement a user development environment for the system. We want to support multi-agents, maybe multi-agent planning or at least messaging. There is work done on anomaly detection in the AOS, and we want to improve the documentation given by the user, and we want to learn it from the robot experience. We want to use machine learning. Thank you very much.